on behalf of Pune. Welcome the people first from Mumbai, including IISER Bombay. It's good to see many of you after a long time. And let's have a very good meeting over 2 days. So the first speaker for the session today is Supriya Pisolkar from IISER Pune. She will speak on towards quantum measure conjecture for biquadratic extensions and example.
Hello, can you hear me? Okay, so I would like to thank all organizers for giving me this opportunity, and actually I am so I was down since there is some echo. Huh.
Try speaking.
Hello. Hello. Still there.
Okay, you start talking. Let me see something. You start talking something.
Okay, so I was a little bit down since yesterday. I have fever, so I was thinking of cancelling my talk, and then now I am here. So let's see whether I would be able to complete my talk or not. Full screen. Okay. So today I will be talking about towards quantum measure conjecture for biquadratic extension. So this is a collaborative work with Ramla Abdul Latif. Towards the end, I will also talk about my other collaborative work with Ramla as well as Marine and Lara. But first, let me start with this.
Yeah, that's also zero now. Nobody know what to do. We have to mute all the participants. Yeah, Zoom volume is mute and machine volume is also mute. I don't know the source of the.
This. Hello. No, hey, banda kela.
I don't know the source of the problem.
This I can actually remember.
Huh.
The connectors are two voltage, one for display and one for lamp.
Yeah.
So turn
Just come here once. Right to turn it from the problem. You know the control. Oh, okay. Try once.
Hello. Hello.
Yeah. Okay. Thanks.
Okay. Thanks. Okay. So.
Close the Zoom participants. If you can minimize it.
Yeah.
Minimize that one. Those pieces. Yeah, exactly. Thanks.
Finally, we can start.
Okay. So I will start with general context of understanding Galois groups. So as all of us know that given a number field K, we are always interested in knowing about what we know or what we can gather about absolute Galois group of that number field, right? So these are objects of interest to all number theorists, and not just for number field but also for function fields. But it's in general a very hard question that how to understand this group, okay, and in fact how to give a group structure of such a group, okay. So there are two methods usually people try. One is direct method to work with elements of this Galois group. Another is use representation theory, okay, to understand this group. So let me start talking about one such group, which is a very interesting group. So starting with a number field k, there is a unique field associated to it, which is called as the Hilbert class field, and it is the maximal unramified abelian extension of k. Okay. It is a fact that such field exists, and of course it's Galois, and if you compute its order of the Galois group, then that is called as class number, and it's always finite. Okay. So these are like milestone results in class field theory. Okay. Now let's talk about class field tower. You start with a number field, take its Hilbert class field, again take its Hilbert class field, and you can go on building a tower. Okay. So that is called as class field tower, and question is whether this tower stabilize within finite number of steps. Okay. So to answer this question, what people tried is, instead of actually working with this tower, they tried to work with this tower, which is a Hilbert P class field tower. So what is Hilbert P class field? It is nothing but the maximal unramified abelian P extension. Okay. So Goulod and Shafarevich answered this class field tower problem negatively. So they said that there exist number fields and primes P such that the maximal everywhere unramified pro P extension L of k is of infinite degree. Okay. So next question is, of course, if there exists such a field extension, then what could be the structure of its Galois group, right? So in 1992, Fontaine and Mazur gave a remarkable conjecture, which is now very celebrated conjecture, called as Fontaine-Mazur conjecture, and most of the modern number theory is actually driven by the theory which is developed to answer this conjecture or to verify the truth of those conjectures. What I am going to display now is not the original statement, but is some version of that statement. Okay. So what they predicted, among many other things, is that certain type of pro-P groups cannot occur as Galois groups of the above extension. Okay. So I asked this question, that what is the structure of the Galois group? Okay. So instead of finding the structure of the Galois group, what one can do, one can try to study groups which cannot occur as Galois groups, okay, of such extension. And that is what is predicted by Fontaine and Mazur, that here is the conjecture. So I am sorry, I will read out. They predicted that there does not exist an everywhere unramified periodic representation of the absolute Galois group of a number field with infinite image. So this is a very strong statement. It says that your periodic representation of, I mean, if k is a number field, then I mean, if you consider everywhere unramified periodic extension of that number field, then its representation cannot have infinite image. Okay. So it has to be a finite group. Okay. So it means that periodic analytic groups cannot occur as Galois groups of such extensions. This is the result that this conjecture is saying, that infinite periodic analytic groups cannot occur as Galois groups of these extensions. Okay. Note that periodic, so this is a result of Lazard, which says that any periodic analytic group has an open subgroup which is a uniform pro-P group. Okay. So pro-P group, of course you all know what is uniform, I am going to explain. Okay. So because of this result of Lazard, one can actually restate this conjecture as follows. So I am calling it as uniform version of Fontaine-Mazur conjecture. So this says that there does not exist a number field k and an infinite everywhere unramified Galois pro-P extension L, such that this Galois group is a uniform group, and that is why I am just calling it as a uniform version. Okay. Earlier the result was saying that it cannot be an analytic periodic group. Now we are saying that it cannot be a uniform group. Okay. So please try to memorize this statement, because the whole talk is going to be revolving around this statement. Okay. This is sort of a negative result. So let me now define what uniform group is. Let me start quickly with some basic definitions. We all know what are profinite groups. It is a limit, inverse limit of finite groups. Example is ZP, which is inverse limit of Z mod Pn. And in fact, if you consider GLN ZP, that is also a profinite group. Okay. Do you know any distinction between these two? I mean, this is a pro-P group, of course, inverse limit of P groups. Do you think that this is a pro-P group? Actually, no. So you can prove that SLN ZP and GLN ZP are profinite groups, but they are not pro-P groups. Okay. So given a profinite group, there is a unique subgroup within that group, which is called as Fratini subgroup. It's the intersection of maximal proper open subgroups of G. Okay. This is nothing but the characteristic subgroup of. You can show that this is a characteristic subgroup of group G. Now given a pro-P group, now I am talking about pro-P groups. Okay. Given a pro-P group, there is a natural filtration within that group given by the lower P series, where I start with P naught G, which is G, and then I go on constructing the other subgroups. Okay. What is P class of G? P class of G is the smallest case such that PKG is actually trivial. Now these are some non-trivial statements. Within pro-P group, if I look at family of finitely generated pro-P groups, then this Fratini subgroup is actually P2 of G. So what is P2 of G? It's G to the power P commutator GG. Okay, and this bar means, because I am working with pro-P groups, this is the closure. Okay. Point is that if I look at the minimal cardinality of the topological generators of this G, because I am saying that it's a finitely generated pro-P group, so I will look at the topological generators, and if I look at the minimal cardinality, let me call it as DG, then this is actually in fact equal to the FP dimension of this. Now why this is a FP vector space? Clearly because if I, as I said, that phi G in this case is G to the power P and commutator GG, right? So if I go modulo commutator, it's a abelian group. If I go modulo P powers, it's going to be FP vector space, correct? So this is same as this, and this is further same as this. Okay. Second is, just like the cardinality of generators, we are also interested in the relation rank. Okay. So given such a finitely generated group, we can write it in terms of its presentation, right? Generators and relations. Okay. So this relation rank is actually given by dimension of H2GFP as a FP vector space. Okay. So this sort of follows by one-side basis theorem, and for this we need spectral sequence. Okay. Fine. So just remember that DG is cardinality of generator and this is relation rank. Fine. Okay. Now let's talk about what are uniform pro-P groups. We say that a pro-P group, or maybe a P group, let's start with a finite P group, it is said to be powerful if one of the things hold. So I'm sorry. Oops. Okay. So when P is odd, we say that G by G to the power P is a abelian group, and when P is 2, we say that G by G to the power 4 is a abelian group. So one can actually think of this being powerful as a generalization of being abelian. Okay, the group is not abelian, but we are saying that the particular quotient is actually a abelian group. Okay, and what is uniform pro-P group? It is a powerful finitely generated pro-P group such that I told you that this pro-P groups has this series, right? If I look at the successive quotients, then the successive quotients should be actually isomorphic. Okay, so then your pro-P group is actually a uniform pro-P group. Of course, we are keen on knowing examples, right? So this is again I am recalling the result of Lazard that I used 2 minutes back. A topological group has a structure of periodic analytic group if and only if it contains an open subgroup which is a uniform pro-P group. Okay. A concrete example is following. You can look at kernel.
You show the previous slide.
Yes. Sorry.
Okay, thanks.
So, a concrete example is the following. You look at the map SLN ZP to SLN Z mod P to the power m for varying m. Okay. You look at its kernel. All these kernels are going to be pro-P groups. This is again a non-trivial statement to prove. Okay. Moreover, you can show that when P is odd, then gamma 1, which is kernel of SLN ZP to SLN Z mod PZ, this is a uniform pro-P group, and for P equal to 2, gamma 2 is going to be a uniform pro-2 group. Okay. Note that for other gamma m's, I mean other than the gamma 1 and gamma 2, they are not uniform because you can prove that they are not powerful pro-P groups. Okay. I said that uniform group is a finitely generated pro-P group which is also powerful group, right. So we will play with this gamma 1 in this talk. Okay. So our goal is to actually try to see what uniform version of Fontaine-Mazur conjecture was trying to tell us. It was trying to tell us that given a number field K, there does not exist a everywhere unramified extension L whose Galois group is actually a uniform group. Okay. So Miguel Boston gave the first evidence of the truth of this conjecture in 1992. Okay. And instead of using representation theoretic techniques, he used purely simple group theoretic techniques, okay, to prove this result. So here is his result, and it's a special case. I mean, he did not prove this conjecture in generality, it's a special case of that. So start with a number field, start with the extension which is a prime degree, so it's a cyclic extension. Now suppose P is a prime such that L and P are co-prime, and further P does not divide the class number of base field. Then he proved that there is no infinite everywhere unramified such extension L such that Galois group is a uniform group. Okay. So there is this condition that P does not divide HF. Okay. Later in 1999, he actually generalized his result where K over F is cyclic of degree n, need not be prime. So here it was prime, right? He generalized it to any degree n, but still the condition cyclic was required where n and p are co. Okay. So as I am saying that we need this extension to be cyclic, the main ingredient is that you consider this cyclic group, consider one of its generator and look at its action on Galois group of L over K. Okay. So I am briefly going to tell you this actually idea of his proof. Actually, I will not need this idea later on, but I thought that it is so amusing that, I mean, most of the time when for these big conjectures, representation theory is used left and right, right? But now I am going to tell you some simple group theory arguments which you will see that is giving this answer. So suppose that now we are starting with contradiction, okay. So suppose that our Galois group is uniform, okay, and then we will try to bring a contradiction to this case that P divides this, okay. Now we know if our Galois group is uniform, then we know what are the properties that we have, correct. So suppose there exists such a uniform group, then by Jasenoff's theorem, we have this exact sequence where this is my bigger, I mean the complete Galois extension L over K. I have this K over F which is a cyclic group, right. I can lift this generator, suppose sigma is a generator, I can take its pre-image here. Now that image will act on the image of this group via conjugation, okay. Now our assumption is that this G L over K, which is this group, is uniform. So you know that it's pro P, it has a L series and so on, right? You can consider G mod Pi's, the successive quotients. So of course, if the lift of this generator sigma, which let me again call as sigma, if this acts on this whole thing via conjugation, it also acts on the successive quotients G mod Pi, correct? And one can actually, with some further argument, can show that this sigma cannot act fixed point free on all the quotients G mod Pi, okay? It means that there exists some fixed point. So I will pick the minimal I so that there is this tau which is in G mod Pi such that this happens, okay? And now I will use the isomorphism between the successive quotient because the group is uniform. So I know that successive quotients are isomorphic, and I can actually pull this, fixed point all the way till G by P2G, which is nothing but G by phi G, okay, which is the FP vector space that we have seen, right? So now I have a, so there is a fixed point which is fixed by this sigma, okay. Now sigma is of order co-prime to P, right? The sigma was here, this is of order co-prime to P. So by Marshall's theorem one can deduce that there exists a cyclic P extension which is unramified inside this L. But then you can also show that there exists a degree P unramified extension of M, of F inside this M, okay. So our criteria was that prime should not divide the class number of F, right? But now we have developed a degree P extension of this F which is unramified, and that gives a contradiction to P dividing the class number of F. So it's fast, I know. So ask me question if you are. The point here is just to tell you that even an undergraduate student can understand this simple group theory arguments, okay. So I mean, okay. So later Farshid Hajir and Christian Mayer in 2017 attempted to generalize Boston's strategy to deal with the case of tamely ramified extensions. Ours was everywhere unramified extensions, okay. Now they tried to play with tamely ramified extension, and they gave the first evidence to the truth of even the uniform version of the tame Fontane-Mazur conjecture. In that case, the challenge was to handle the fixed points which will be introduced by the ramification, okay. So let me just flash this, I will not speak about it. So suppose K is a number field, then there does not exist a finitely tamely ramified Galois extension L over K whose Galois group is a uniform group, okay. That is why I am calling this as a uniform group. Please note that wherever I am saying uniform version, so there are actually statements like just tame Fontane-Mazur conjecture which are deduced from the original statement of the conjecture, which I am going to talk about in the later part of the talk, okay. So this is just the uniform version, okay. Now this was the Boston's result. What we are going to build on is the following, okay. Here is an example of Bale which was supplied to Boston in, this example was actually mentioned in Boston's paper only, 1992 paper, and he said that okay, take a biquadratic extension this, take P to be 3, then actually you can show that 3 divides class number of K. Now 3 is a odd prime that divides this, and actually this violates Boston's hypothesis, okay. You can actually show that its class group is this, so of course 3 divides the order of this group, and he asked the question, okay, because a hypothesis is violated, can you actually compute Galois L over K of this K? And if it turns out to be a uniform group, then you have a counter example to Fontane-Mazur conjecture, correct? Yes. So he just mentioned this in his paper, and nothing was done further that. So with Ramla, what we tried to do is we considered this short exact sequence, okay. Now our goal is to actually see whether this G is uniform or not, and whether it gives a counter example or not, okay. So this short exact sequence gives following Box-Time map and cup product map. And this is a result of Andorski's and Chvetko, which says that for a infinite finitely generated Propy group, if these two maps are isomorphisms, then your group has to be gamma 1, and I told you that gamma 1, which is kernel of this, is actually a uniform group. Okay. So what we can do is we can try to verify, in our case, instead of this G, we can take our Galois group L over K, and if we could prove that both these maps are isomorphism, then we are done, because then we know that our group is uniform group. Yes? Okay. Please recall that I told you that DG, the generator rank of G, is actually dimension of this H1, correct? And relation rank was dimension of this H2. Okay. So for this particular biquadratic extension, actually one can verify that dimension of this, FP dimension of this is 3, and FP dimension of this can be 3 or 4. Okay. What we could do is that we could prove that both these maps are injective maps. Okay. So we could reach to that point, and then we know the dimensions. Okay. So if we could prove that dimension of H2 here and here is 3, then we are done, right? Yes? Okay.
Can you go back 2 slides? I missed what the definition of G was. What was G on the previous slide?
Here?
Yeah. So the Galois group of a maximum of the okay. Thanks.
Okay. So our goal is to now check injectivity and surjectivity of these maps. Okay. Okay. So here is our theorem. So we could prove that cup product map and Box-Time map are both these maps are actually injective. Proving this was a straightforward argument, but proving that cup product is injective was very hard, and we couldn't do it with any, with the theoretical techniques that we both were aware of, we couldn't do it. So we started working out with Sage and Pari GP, and somehow we could do the computations, and actually those computations gave us the proof for the cup product of the injectivity. Okay. So what are the techniques? Those are going into the computations that I am also going to explain. Okay. What is the consequence of this? Consequence is that, so this is a Linnell's result, which says that if cup product map is injective, then your group has to be a powerful Pro-P group. Okay. So at least we could prove that it's a powerful Pro-3 group. And then again by using Magma, Gap, Pari GP and Sage, all these tools, we could actually prove that Galois group that we were looking for is actually a finite group. Okay. It's a finite group of order 6, 5, 6, 1, and its rank is actually 4. We wanted the rank to be 3, but the rank is 4, so those isomorphisms are not there. And if you pay attention, proving that that's not a isomorphism will prove what? It will just prove that my G is not gamma 1, right? That doesn't mean that it is proving that it is not a uniform group, right? Because there are several other uniform groups, correct? But point is that because of these computations, we could actually show that it cannot be a uniform group, it is just a finite group. And over Magma, we can actually give the explicit presentation of this group, okay? And hence, we settled this question that this is not a counter example to Boston's result. Okay. What is the another byproduct of this? In our example, we said that 3 divides the class number, right? And that hypothesis was there in Boston's result, that P does not divide the class number. So in fact, this result says that that condition in Boston's Boston's result, this is not a necessary condition, correct? So you can still, that hypothesis is violated, and still we could prove that the group is not a uniform group. Okay. So now I am going to quickly give you a glimpse of what exactly went into the computations that we did. Okay. So for our computations, we needed to do lots of computations of class groups of certain number fields, and for that you need to use magma, and whenever you are using number theoretic techniques in magma, underlying is the assumption of GRAs, okay, generalized Riemann hypothesis. And so I would like to say that because we have used all those commands and packages, actually our results are dependent on GRH, okay.
This counterexample, F was Q. If you were to compare with that, Came of Boston, you want to take F to be Q?
Q,
K
yes,
to be this, and L is going to be the Galois group of
correct.
the maximum ramified.
Pro 3 extension. Now this is quadratic, so this is degree 4, which is co-prime with the Pro 3, so the 3 part.
So L was a P.
So L is a 4, L is 4 here.
L is 2 or 4?
4,
4. Okay.
L is 4. In fact, you can split this into a quadratic over quadratic to keep the hypothesis of the extension to be cyclic. I mean, this degree 4 can be seen as a 2 over 2 thing, and here L over K can be seen as a over degree 2, that is also. Okay. So we have used this O'Brien tree algorithm. What is very fascinating about this algorithm is that if you give me any finite pro P group and you know that its generators are D many, okay, suppose you have a P group and there are D many generators, actually this algorithm tells you that you will be able to find your group G, whatever it is, somewhere on this tree. On this tree which is rooted, which is started at elementary abelian P group with D many factors, okay. So let us see. So to construct such a tree, I will say that groups G and H are connected by an edge if H is a quotient of G, okay, and now G is a pro P group. So I have this lower center series. So H is a quotient of this G by this subgroups, and the P class of G is K plus 1, okay. So when you see it first time, it appears a very technical condition, but it is very easy. It just says that G and H are connected if H is a quotient of G and P class of G is actually bigger than H. That's it, okay. And whenever you have this condition, you can start drawing edges among such groups, okay. So P class is where the P central series, you have this chain, right? G is P naught G, then P1 G and so on. It is the smallest case so that PKG is trivial. So whenever you can draw an edge, you can say that G is a descendant of H. Moreover, you can say that it's an immediate descendant or a child of H. So this is little counterintuitive because you are saying that H is a quotient of G, but you are saying that now G is a child of H, okay. So G is a child of H if actually P class of G is just one higher than the G class of H, then it's called as an immediate descendant, okay. Example, only P group of class 1. So you can ask, okay, now that you are talking about P class of G and so on, give us one example. So only P groups of class 1 are elementary abelian P groups. So this is a magma notation of CP cross CP cross CP, okay, which is square bracket PPP. And any P group G will be a descendant of this if its abelianization is this, okay. Take any group in the world whose abelianization is this PPP, okay, and which is itself a pro P group. You can draw an edge between these groups, okay. What was our goal? Let me recall. Our goal is to actually find out what that G is, okay. We wanted to give the explicit presentation of our group, okay. So but we don't have any information. We just know that it's a Galois group, okay, and we can compute over magma its abelianization, its class group, okay. That's the only thing we can compute. So instead of finding G, what one can do? One can go on finding the quotients G mod PIGs. Correct? Once I have quotient, there is a hope to build and get some information about G. Correct? But again, if I don't know G, how can I know about PIGs? Correct? Yes, so that's a thing. So what this tree algorithm is doing, I will start with G mod P1G, which is the abelianization, that I know. To go to G mod P2G, what I will do, I will look for all the groups in the database which are Pro3 groups and which will satisfy certain conditions and which can act as G mod P2G. Okay. For each such candidate, I will go on looking for its descendants and so on. Okay. Finally, I will get a big huge tree and I will start pruning down the tree. So, I will start chopping down the tree because I want to find my G on one of the branches, right. It can't be everywhere, correct. So, I have to go on making clever choices by applying filters. Okay. So here is the position of the problem. This was my field. I will denote G by PCG is this, and goal is to find the quotients QCG instead of finding the group G. Okay. What do we know about this alien group G that we would like to find? It's abelianization. By the arguments coming from Boston's work, we know that there is a Klein 4 group sitting inside odd G. Now, this condition is a non-trivial condition which we have actually found out while proving the injectivity of the cup product map. Okay. So, this is a non-trivial result. We could find out that there are 13 maximal subgroups, maximal meaning now we are Pro3 extensions, so index 3 subgroups of this Galois group whose abelianizations give this pattern. So, there are 13 such, so their abelianizations are C3 cross C3 cross C9 appearing 4 times and C9 cross C9 appearing 9 times, and we will use this, and this has played a really crucial part. How to build a tree? We will find all possible H such that H can act as this QCG, and what are the filters that this should satisfy? Its abelianization also has to match with the abelianization of G. It should also contain Klein 4 group. Now, there is this bit technical condition of the P multiplicator rank and so on, which let me skip, I will not talk about it, but whatever this number is, this has to be less equal to RG. This is again a big theorem. This is a result of Boston and Nauer proved in 2020, okay, in Nauer's thesis. So, we have used that, and we know that abelianization of maximal subgroups of QCG can be no bigger than that of G. So, here is this pattern, right, that I have written down. Point is that QCG's maximal subgroups cannot have abelianizations bigger than this. Now, let us start applying these filters. So, here is I am building the tree. Q1G is my C3 cross C3 cross C3. This is the root of the tree. Now, I want Q2G, which is G mod P2G. I will find out all possible groups, okay, satisfying all the filters. So, we found that there are 79 actually total descendants of this. For each of the 79 descendants, we could compute their class group and all the filters we could apply on that, and we could see that actually it boils down to only 6 possible candidates for Q2G. Now, here I am writing this angle bracket Ni for the ith group in the small group library of GAP. So, in GAP there is this actually very fantastic package which is called as small group library, okay. And what does it do? It has the database of all the groups of certain orders, okay. So, suppose group has order n, okay, then this n will stand for that order and I will stand for the index in that list of groups of order n, okay. So, if you type this command, let us say 243, 40, it means that this is a group of order 243 and there are many groups of this order, and this is the 40th group that I am looking at in that list. So, it is actually going to the library and finding out something, okay, from the list. So, if you type this command, it will actually give you generators, relators, tell you whether it is solvable or not, everything that you need to know about this finite group. So, it's really a very nice package. So, we could get that there are these 6 groups which could possibly occur as this Q2Gs, okay, meaning the quotients G mod P2Gs, okay. How to rule out all except one, right, because I want to find G's somewhere which will occur in one of the branch, right, every group will occur uniquely somewhere, okay. So, repetitive application of filters will give me that I can exclude in between these groups. To give you the idea of complexity, if I work with this, how to exclude that G is not on the further branch of this, is that I have to study the descendants of this. Okay, I will look at all the groups which are quotienting on this, okay, and has class number 1 bigger than this. There are 207 groups for just this. For those 207, we computed all their maximal subgroups, we computed their class groups, and we could see that they don't follow the pattern that we expect them to follow. So we can rule out that. Okay. Finally, I am throwing many things under the carpet. We could see that it actually appears as a 9th descendant of this group. Okay, 729, 132. And once you spot your group on this tree, in Magma you can actually easily then tell that, okay, this is the D9, 9 descendant. So there is an easy command on Magma which says that descendants of G, it will give you in a flash all the descendants. If you tell me the 9 descendant, it will give you all the generators and relators. Okay. So you can explicitly know what your group is. So what I showed you is a prune tree. Okay. I already removed many of the things. But if you look at a crude tree, it will look like this. This is the root. These are the Q2Gs, then these are the possible Q3Gs, and it will go on. So point is that if you give me a finite T group, it's obvious by the construction that you will be able to find it here because you are finding the quotients, right? Question you can ask is if my group is infinite, because a priori I don't know what my group is, right? If it's an infinite group, will I be able to find it here? So the answer is if you have an infinite propy group, it will occur as an infinite end of one of the branch. Okay? But that is still okay because you know all its quotient, right? So with the limiting argument, you can say something about your group G, okay? Because you know the information about the finite quotients. Okay. So this work we have just submitted, and of course the immediate projects are the following. Why just work with that particular biquadratic, right? Now that we have worked with so many codes and so on, we could actually easily see some patterns. So we have started with working with family of biquadratic extensions, and in fact we have spotted down some of the fields which might violate Fontaine-Mazur conjecture. Might violate in the sense just like what the example Boyle gave, but might in the sense that we still have to compute their group just like we have done. It might, if it turns out to be uniform, we have a counter example. If it's not, then that's not a counter example. Another thing is, as I said, that this condition P not dividing the class number, this is not a necessary condition. This is what we have observed. So now we are writing a completely different proof. So Boston gave this first evidence of the Fontaine-Mazur conjecture, and we are writing a different proof of this result without assuming this condition, and we are also using purely group theoretic techniques. Okay. So now to put everything in the perspective of the original Fontaine-Mazur conjecture. Okay. So let me now start with what was the original statement. Okay. So this was the original statement. So P is a prime, K is a number field. What is definition of a geometric representation? A periodic representation is said to be geometric if it ramifies only at finite number of places, and for each place V, which is over P, the restriction of G to the decomposition group is potential semistable in the sense of Fontaine. Okay. So this condition is to say that it's DRAM and hence Hofstede. So this says that this is the definition of a periodic representation being geometric. Okay. Here is conjecture. This is the original statement. Okay. An irreducible periodic representation of GK is geometric. So geometric in this sense, if and only if it is isomorphic to a subquotient of ethyl cohomology group with coefficients in some Tate twist of a projective smooth algebraic variety over K. So for those, I mean the students I can see who don't know many of the terminologies here, you can just remember that it just says that a representation, a periodic representation is geometric if it comes from actually the étale cohomology groups of some algebraic variety. Okay. So, geometric in different sense, and if it comes from actual in the sense of algebraic geometry. Okay. One way was actually already known. So, if it is coming from the étale cohomology, then it was known that both these conditions of the being geometric are satisfied. So, coming from algebraic geometry implied geometric, that was known. So, the main point of this conjecture is this geometric implies this. Okay. So, let us see what is known about this conjecture. So, for any field k and n equal to 1. So, this is a representation I am talking about, correct. So, now I am talking about one dimensional representation. So, for any field k and n equal to 1, this is known by class field theory. When k is q and n is 2, so 2 dimensional representation, this is the result of Kissin and Emerton. Independently they have proved, I mean cases of this. And third is in the case when k is a CN field, and there are some more technical conditions that pth roots of unity are in the real subfield of k and so on. Okay, I do not remember exactly what are the technical conditions here, but this is a result of Wingberg. So, this result was proved in 2002, these results, I think Kissin's result was in 2009 and so on, and I think this is pretty much we know. I mean the conjecture is still far wide open. Even I mean as you can see for k equal to 2, we just have information about n equal to 2. Whatever we know, actually that theory comes in two flavors, wild case where we have p times above p are in S. So, what is this S? Let me just go back. If you see, it says that this geometric means that it ramifies only at finite number of places, right. This is I am talking about. So, two cases, because I am considering periodic representation whether this p is in S or p is not in S. If p is in S, it is called as wild case. If it is not, it is called tame case, and all these results are actually revolving around these two cases. Hardly anything was known about when S is phi, empty set. So, when I say S is empty set, meaning that we are dealing with everywhere unramified extensions. Okay. So, if you remember, since the beginning of the talk, the results of Boston and all that I am talking about, they were dealing with the case S equal to phi, everywhere unramified case. Okay. Let me just mention what was the tame Fontaine-Mazur conjecture. I mentioned you the original statement. Now, this tame case, suppose this is a periodic representation which is unramified outside S, where S contains no primes above P and S is finite. I am sorry, then this says that then the image of this row has to be a finite group. Again similar to what we have seen for the earlier version. Okay. There is also a uniform version, just like we have seen earlier. It now says that there does not exist finitely tamely ramified Galois extension L over K whose Galois group is a uniform group. Now, okay, we have introduced this finitely many ramified points here. Point is that I mentioned you about Hajir and Mayer's work, right. This was the conjecture what I displayed there at that time, okay, and they were the first one to give evidence for the truth of this conjecture in 2017. And what we have discussed about was S equal to phi case, which was not covered in the earlier work. Okay. So, this was our statement, and this was the uniform version of that. I am just displaying it so that coherently you can see. Okay. Question is, there are so many versions of this. Is there any relation to these versions? Okay, starting from the original statement. So, this is my joint work with Ramla Abdullatif, Marine Renaud and Lara Thomas, and we studied that actually tame Fontaine-Mazur conjecture, I mean tame Fontaine-Mazur conjecture if and only if the uniform version of tame Fontaine-Mazur conjecture, this is what we have proved. We also proved that how class field theory implies n equal to 1 case of TAME quantum is a conjecture, and we further studied how the group theoretic techniques, because in the TAME case it's the work of Hajira and Mayer, right? So we studied how these group theoretic techniques have played a role overall in this actually theory. So these are not, so to speak, very new results, whatever we have done in this work, but they are the missing links in the literature. So people were knowing that okay, n equal to 1 followed by class field theory, or experts were saying that okay, TAME quantum is a conjecture is same as uniform TAME quantum is a conjecture, but it was nowhere written clearly. There was no concise statement to that. So what we have done is that we have actually written down all those missing links in the literature, and this is to appear in Proceedings of Women in Numbers. So these are some of the references. Thank you.
Thank you. Any questions from the audience?
So the uniform version implies the Galois.
Hello. So here, sorry. So this result says that you are starting with, you want to know the pro P extension, and for that prime P you need the condition that P does not divide the class number of the base field. And here what is happening is that we are taking K to be this biquadratic extension, so it's degree over F. Now my F is Q, which is 4, and now I am taking P to be 3, and now this 3 is actually dividing the.
And the conclusion is the same, that there is no uniform.
Yes,
It's just
conclusion
the
is
properties are different.
correct. So we are now trying to give a different proof of this, because this condition is not necessary now. So
In the way Boston used this condition is through Mashka's thing.
yes, that was a very, I appreciated that a lot, because it's just the simple representation theory that he used there. So yeah. And to be frank, I never actually used computational number theory before. For this project I started learning, and to be frank, I'm now addicted to it.
Can I see the next slide where there were some mappings on H1 and H2? G is any infinite finitely generated pro P group such that these two conditions happen. And is this what you are going to use to construct the counterexample?
No. So actually, for the other families, you are saying?
You have the potential counterexamples to Fontaine measure,
Yes.
and those counterexamples
Yes.
come using this theorem.
Yes. So we proved that actually the group or the field that we are looking at, its Galois group doesn't actually give a counterexample. That's what we actually verified. We thought that it's coming closer to giving a counterexample, but then we verified it's not a counterexample. And for that we use this, because we thought that if it is a counterexample, then let's try to check whether these two conditions are satisfied, then we know that it's a uniform group. So we first tried with like naive approach of actually proving that these two maps are surjections.
So one of them goes wrong
So actually both these are injective, but they are not surjective.
in your situation.
Yes. And
Not injective but not subjective.
yes, and that just says that this group is not gamma 1. it doesn't say that it cannot be a uniform group. So there are lots of possibilities for a group being a uniform group, right? Lots of examples. So this is very specific example, and we thought that this will do everything for us because the dimension of this is also 3. SL21, its dimension is 3, and this group to start with also of dimension 3. So we thought that this will be a easy way to go about it, but we could prove that this is not a, there is no isomorphism.
The first mapping is an isomorphism, but the second is only injective.
No, in both the cases it's not an isomorphism. Here the dimension over F3 is 3, here the dimension is 4. Similarly, if you see the product dimension, it is again 3, and this is same now, so dimension is 4. So although it's an injective map, it's not surjective. But the computations helped us in proving that it is actually a finite group. So it cannot occur as even any other uniform pro-P group. That's what we proved.
Oh, it's a finite group.
Yes, that's what we have proved. So here, sorry, this. Here we proved that actually this is a finite 3 group of order this, and its rank is 4. That's what we actually proved.
And that's it.
That says that there is no other, no other, it cannot be any other uniform group also.
But you use some software to do that?
Yes, yes,
It's not a theoretical proof?
no. So we had to use the computations of class groups of various fields, and then you have to use packages. So
There are techniques in pro-P groups to prove it is finite, no?
to prove something is finite,
More relations than generator. I mean, there is some, the way Golod-Shafrovich works,
so Golod-Shafrovich actually,
that it is infinite, but also there are techniques to prove it is finite, no?
so that is for a very particular case. So Golod-Shafrovich inequality says that DG is always less equal to RG, the relation rank, which was anyway satisfied in our case. 3 is less equal to 4. But we couldn't, we wanted to check whether our DG is actually equal to RG. So that we could not do. So here this is DG and this is RG exactly. This is 3, and we knew that this is either 3 or 4 by Golod-Shafrovich. There was other technique. So we could prove that because of the injectivity of the cup product, we could prove that this is a powerful pro-3 group. Okay. So if you remember, a uniform group needs to be a powerful pro-3 group. So one can ask in which case the converse is true. Okay. So point is that if a powerful pro-3 group is actually powerful, pro-P group is actually torsion free, then it's uniform. So torsion free plus powerful gives uniform. So we also tried to prove that our group is torsion free, but that was also very hard because we thought that we already have this.
Your group is finite, so it is not torsion free. It has torsion.
Yeah, but earlier we did not know that our group is going to be finite. So
Any other question from the audience?
Not a question, but is it possible to post the slides? Is it possible to post the slides?
oh yeah, sure, yeah.
Sure, there are techniques in algebra which try to prove that some algebras have 0 dimension by I will have to look up Said's book on.
Galois homology.
Yeah, there are not methods to prove something is finite.
No. We have been, looking at this book like a Bible.
Anything that he writes. Yeah.
Okay, let us thank the speaker.
Thank you.
check. Hello, check. thanks for the organizers for giving me a chance to speak in Mumbai-Pune number theory seminar. So the title is Blobs in Rigid Analysis. So rigid analysis was invented by Tate in 1960s to study analysis over p-adic number fields for which the topology is totally disconnected. So the classical techniques can't be used over there. And as a consequence of rigid analysis, Tate proved a p-adic uniformization theorem for elliptic curves with semi-stable reduction. And then that led to a huge branch of mathematics. For instance, L invariants can be defined using the p-adic uniformization and so on, MTT. Yeah. So that's rigid analysis. And nowadays rigid analysis shows a lot in number theory. For instance, it shows up in the problem of computing reductions mod P of semi-stable representations. Semi-stable representations and crystalline representations. So there is a relation between their reduction mod P, and rigid analysis helps us to connect them. So we have in a recent work, which is a preprint, so in a recent work, a joint work with Professor Ghate and Yasuda, we were able to explicitly connect semi-stable representations with crystalline representations. So there is this word limit. So where is this limit taken? This limit is taken in a rigid analytic space, which turns out to be the blow up of certain rigid analytic space parametrizing characters of QP star, continuous characters of QP star. So today we won't be looking at this, but we will be looking at a baby example of blow up, rigid analytic blow up of a plane at a point at the origin. So yeah. So the fundamental object in rigid analysis is the Tate algebra. So a Tate algebra in n variables. Tn is the notation for the Tate algebra over QP. Over QP is important. Over QP. Denoted by QP diamond S1 to Sn is the set of all power series such that the coefficients go to 0 in the p-adic topology. So for instance, you can substitute for S1 to Sn any integral elements to make sense of this sum. So this Tate algebra is a fundamental object in rigid analysis, and we would be looking today at the space SPA of T2, which is a two-dimensional ball. So by this notation SPA of T2, I mean the set of maximal ideals in this algebra. And we will be blowing up X at the ideal I given by S1, S2. So the origin. This is the origin. If we look at the e-valued points of part E2 for any finite extension E, it turns out it's 2 copies of the ring of integers in E. So one can picture X as a square, and here is the origin given by the vanishing set of I. We will be blowing that up. Yeah. So notation. So let I tilde be the ideal sheaf on X corresponding to the ideal I. So just like in classical algebraic geometry, if you have an affine space, affine scheme, spec R, and if you have an ideal of that R or any module of that R, then you can do this construction M tilde. What is called M tilde in Hartshorne. On each basic open set given by non-vanishing of F, the sections are the localizations of the module at F. A similar construction can be done over here. So let's call that sheaf I tilde. Yeah. So the whole point of blowing up is to somehow make this ideal I principal. So formally, a rigid analytic space X tilde with a map pi from X tilde to X is called a blow up of X at the origin if, just as in the classical algebraic geometry case, 2 conditions are satisfied. The first one is that the inverse image ideal sheaf is invertible. What does invertible mean? Stocks are generated by non-zero divisors. And the second condition is that there is a smallest such space in which something happens. Smallest such space in which the extended ideal is invertible, which formally means given any rigid analytic space, Y with a map to X, let's say F, and X tilde is this with a pi, such that F inverse I tilde OY is invertible, then there exists a unit G from Y to X tilde such that the diagram commutes. This diagram commutes, just as in the algebraic geometry case. Yeah. So to give a blow up, first we need to give a candidate for X tilde. We want to find the blow up of X at the origin. So we need to first give a candidate for X tilde and a map from X tilde to X satisfying the first condition, and then we need to check the second condition. So let's look at the construction of X tilde. Yeah. So the idea is you keep this picture in mind. So there is a sphere, only this hollow sphere, not the filled sphere. Then there is this north pole, there is this south pole. We will take open balls around the north pole. So these, and then we will take open balls around the south pole, so horizontal ones. and we'll glue them together as we go on. So we'll increase the size of the open ball centered at the north pole. We'll keep on increasing it. Then we'll keep on increasing the size of the open balls around the south pole, and then we'll get a space after gluing. So formally, we'll choose 4 indeterminates. Just some variables. Now, for each I greater than or equal to 0, set AI to be the affinoid algebra QP S1 S2 P to the I Q1. So this should be thought of as a Tate variable. This whole thing should be thought of as a Tate variable. Mod S2 minus Q1 S1. So here we are making it so that S2 is divisible by S1, so that when we extend the ideal I to this AI, the extended ideal becomes principal. So SPA AI is a subset of SPA T2 consisting of maximal ideals M such that S2 mod M is less than or equal to P to the I S1 mod M. So what do I mean by this? So M is an ideal of T2, right? T2 is just QP S1 S2. If we go modulo any maximal ideal, we land inside a finite extension of QP, so that we can take the norm, but the identification between T2 mod M and the finite extension of QP is well defined up to Galois conjugacy, so that the norm makes sense. So therefore S1 mod M and S2 mod M makes sense. Just look at the image of S1 under that map, so it would be some periodic number, take its norm. Yeah. This can be seen from the point that the norm of P to the I Q1 is less than or equal to 1. It turns out that these state variables have norm less than or equal to 1 always. Yeah. So pictorially, you should think of this, the vertical stripe thing, as SPA AI. So now you can see that we get a chain of maps. This, as I goes on increasing, this condition becomes loosened a bit. If if we increase I, then more maximal ideals satisfy this condition. So SPA A0 is smaller, then SPA A1 is bigger, SPA A2 is bigger, and so on. Yeah. Yeah. So and of course dot dot dot. It turns out that each smaller one, this smaller affinoid space is an affinoid subdomain of the larger one, a Weierstrass subdomain. And therefore we can glue all of these spaces together to get a rigid analytic space, and which we call V1 tilde. So pictorially, you should think of V1 tilde as the sphere minus the south pole. This SPA AI goes on increasing, and their union is everything minus the south pole. Yeah. Similarly, define BI to be QP adjoint S1 S2 P to the I Q2 mod. Now here we'll make S1 divisible by S2 and do the same construction. spa bi consists of maximal ideas m of T2 such that now this condition is flipped. Norm of S1 is less than or equal to p to the I norm of S2. So the region denoted by horizontal stripes, you should think of that as spa bi. So yeah, reciprocal of this pi hai. And as you go on increasing I, this spa bi goes on increasing. And similarly, you can, similar to the AI case, you can glue all spa bi and define whatever you get to be V2, V2 tilde. So pictorially, as you might have guessed, V2 tilde is sphere minus the north pole. You see, as spa bi goes on increasing, it never touches the north pole, but you can cover everything except the north pole. Yeah. And now, so this is the picture of x tilde. We want to glue V1 tilde and V2 tilde along some certain open subvarieties to define x tilde. That's the point. So let us define these open subvarieties. Yeah, they would come later. Now, just now. Yeah. That will be the candidate for the blow. Glue V1 tilde and V2 tilde along certain open subvarieties. Now, so pictorially, can you see what those subvarieties will be? So V1 tilde is a sphere minus the south pole, V2 tilde is a sphere minus the north pole. So you want V1 tilde prime and V2 tilde prime to look like the sphere minus the north and south poles, right? So just as we did for the entire sphere, sphere minus the north pole, we started with open balls around the south pole and took their union. Similarly, we will take these annuli, these checks annuli, and we will increase these annuli to get V1 tilde and V2 tilde prime. Sorry. Yeah. So now for the same index set, define AI prime to be S1, S2, P to the I Q1, P to the I Q1 prime. So here's where Q1 primes and Q2 primes would show. Yeah. So we introduce an inverse of Q1 as a Tate variable here. So therefore, spa AI is a subset of spa AI consisting of maximal ideals M such that the norm of Q1 is greater than or equal to P to the minus I. You see, spa AI has the condition that norm of Q1 is less than or equal to P to the I, and introducing this new variable, we have made the norm of Q1 to be greater than or equal to P to the minus I. So it's an annulus. Yeah. So again, spa A naught prime, spa A1 prime, and so on. These form an increasing chain, and we can glue all of these spaces together to get V1 tilde prime. Now the claim is that V1 tilde prime is an open subvariety inside V1 tilde. So how does one check that? It turns out by common sense also, but it's precise that V1 tilde prime is open inside V1 tilde if its intersection with the charts of V1 tilde are open, right? So you intersect V1 tilde prime with the constituents of V1 tilde, which has spa AI, and if you are able to prove that this intersection is open inside spa AI, then it turns out that V1 tilde prime is open inside V1 tilde. Yeah, but it just so happens you can check that. You can check using this condition that V1 tilde prime intersecting with spa AI is the set of maximal ideals M of AI such that so what happens if you take the limit of these conditions, you just get that Q1 mod M is strictly greater than 0, right? So you see, this is the Zariski open set. This is a Zariski open set given by the non-vanishing of Q1, and it turns out that Zariski open sets are admissible open in the topology of rigid analysis, and yeah, therefore V1 tilde prime is an open subvariety of V1 tilde. Yeah. May I erase this? So similarly, define Bi prime to be Qp S1 S2 P to the I Q2 P to the I Q2 prime modulo this ideal. It's analogous, right? And glue spa Bi prime to get V2 tilde prime. And again, by that logic, by a similar logic, V2 tilde prime is an open subvariety of V2 tilde. So pictorially, this region, this much, this region is spa AI prime, and the same region but as a subset of Bi is spa Bi prime. So we want to identify these subsets together, these annuli together, and therefore we need to find an isomorphism between spa Bi and spa AI. So to get an isomorphism between spa AI prime and spa Bi prime, you just have to give an isomorphism between AI prime and Bi prime. So what should you do? So S1 goes to S1, S2 goes to S2, and what happens to the QIs? You want to map this way, so send S1 to S1, so don't change these base coordinates, but send Q2 to Q1 prime and Q2 prime to Q1. Q1 prime is the inverse of Q1, so we are just flipping these Q coordinates. Yeah, you can see that these equations now flip. This S1 minus Q2 S2 and S2 minus Q1 S1, these equations flip, and this equation transforms into this equation, and it turns out that this map is an isomorphism. Yeah. Therefore, get an isomorphism from spa ai prime to spa bi prime. It turns out that you can see that these are compatible. If you change I, these isomorphisms are not really changing. So it turns out that all of these isomorphisms are compatible and they can be glued together to get an isomorphism between V1 tilde prime and V2 tilde prime. Yeah. So therefore, we have identified V1 tilde prime and V2 tilde prime, and those are open subvarieties inside V1 tilde and V2 tilde, so we can glue them together and define X tilde to be the space obtained by gluing these two together. So you can see pictorially X tilde is this sphere. Yeah. So that's our candidate for X tilde. Now, one interesting thing is that this construction is, even though it's not analogous to usual algebraic geometry, it turns out that the E value, so if E is a finite extension of QP, then the E valued points of X tilde are the same as those obtained from, you can expect from algebraic geometry, little s1, little s2. So the usual definition that you can find in Hartshorne is the regional analytic space obtained by gluing V1 tilde and V2 tilde along the primes. Yeah, that I am going to define, but it's the obvious one. So these are the E-valued points of X tilde. So this matches well with the usual algebraic geometry. Now, the map pi from X tilde to X, the blow up map. So again the same trick. X tilde is given as the union of spa ai's and spa bi's. Therefore, to define a map pi from X tilde to X, you can just define it on spa ai's and spa bi's. So let's start with spa ai. You want this map spa ai to X, but what's X? X is spa of T2, right? T2, or explicitly QP S1 S2. So you want a map from QP S1 S2 to AI, right? But if you recall, AI is here. QP S1 S2 P to the I Q1. So there is an obvious map, right? From QP S1 S2 to AI. Send S1 to S1 and S2 to S2. So that's the map. That's the restriction of pi to spa AI. Turns out that these maps are compatible between all AIs and the flip between AI and BI, and therefore these maps glue together to give you a map pi from X tilde to X. Yeah. Yes. Yes. Yeah, it was here, sorry, I erased it. Yeah. When it's the same as the construction of P1, right? You take two copies of A1 and you identify. What? No, can you? Yeah. Yes. No, so this is just a pictorial representation, but explicitly it's the generic fiber. So it's the fiber above 0, 0, 0. So these are just representations, how to think about it. These are not precise spa AIs and spa BIs. I mean, the same thing happens in. Yeah. So uh, that's the space X tilde and the blow up map pi. And now we have to check these two conditions. Yeah. So maybe this is fine. So we have to check this condition 1, that the inverse image ideal sheaf of I tilde when taken to X tilde is invertible. Yeah. So what does invertible mean? I repeat the definition. Means all the stalks of this sheaf at all points of X tilde are generated by a non-zero divisor. So it's a local condition, right? To obtain stock, you can restrict the sheaf to an admissible open and then take its stock. It would be the same as taking the huge stock of the entire space at that point. So, yeah. To prove that phi inverse I tilde OX tilde is invertible, enough to show that pi restricted to, let's take spa AI for the time being, inverse I tilde, yeah. To prove that the huge sheaf is invertible, it's enough to check that its restriction to spa AI is invertible. So what do you have here? You have a map phi restricted to spa AI, and just think of it as pi, from spa AI to S1, S2. Here you have an ideal I corresponding to the ideal sheaf I tilde. You pull this back, pi inverse I tilde O spa AI. So everything is affinoid, right? So this is also tilde of some ideal. Which ideal? The extended ideal. And so to prove, yeah, to prove that this ideal pi inverse I tilde O spa AI is invertible, you have to prove that I AI tilde is invertible. Yeah, but it turns out using some faithfully flat descent kind of thing, kind of arguments between the localizations of AI at various maximal ideals and these talks, it's enough to show that AI localized at M yeah, it's enough to show that the localizations of the ideal are generated by non-zero devices for all maximal ideals. Yeah, but many of you have seen that the map from let's say a ring to its localization is flat, right? Localization is flat, and under flat maps, regular elements go to non-zero devices go to non-zero devices, because you can take multiplication by a non-zero divisor map. Under flat base change, it would still be injective. So to show that AIM is generated by a non-zero divisor, it's enough to show that IAI is generated by a non-zero divisor. And yeah, you can see from the presentation of AI that the extension of I to AI, which a priori is generated by S1 and S2, is actually generated by S1 because S2 is divisible by S1 in AI. So this is just S1 AI, right? So all we need to do is that we need to check that S1 is a non-zero divisor. That will prove that AI is generated by a non-zero divisor. The argument goes further. Yeah, so here comes, so here I'll assume some things from periodic analysis. So we have to prove that S1 is not a zero divisor. In AI for all I greater than or equal to 0. So you can see from the definition of AI that as I goes on increasing, AI, the ring AI becomes smaller and smaller. Therefore, it's enough to show that S1 is not a zero divisor in A naught. So let's do that. Yeah. So suppose H is an element in QP S1 S2 P to the 0 Q1 such that H times S1 is 0 inside A naught. What does it mean by 0 inside A naught? It means that the denominator divides H times S1. S2 minus Q1 S1 divides H times S1. We will be proving that H is 0 in the quotient A naught. So usually in algebraic geometry, what do? You apply the division algorithm, right? These are all polynomials. So you can apply the division algorithm to H and S2 minus Q1 S1 and then do the remainder trick. Here also you can do something similar, but it's slightly more delicate. You need to use the Weierstrass division algorithm. Notice that this element is S2 distinguished of degree 1. What does it mean? So this you take this power series, which is a priori in 3 variables, and write it down as the power series in S2. So the coefficients are power series in the other 2 variables, Q1, S1. The constant term is Q1, S1, the linear coefficient is 1, and so on. The rest terms are 0. Distinguished of degree 1 means that the coefficient of S2 to the power 1, the linear term, is the unit. It's a series in Q1 and S1, so it makes sense to talk about it being a unit or not. It's not a vacuous condition. Here it's 1, so it's a unit, then the norm of that coefficient is the same as the norm of the huge series. The norms here are the Gauss norms, means take the supremum of the norms of coefficients of all of these elements. The Gauss norm here is 1 and the norm of the coefficient of S2 is also 1. So that condition is also satisfied, and the final condition is that the higher coefficients should have smaller norm than the norm of this S2, coefficient of S2, which is satisfied, right? Higher coefficients are 0, so they have 0 norm. So it turns out that S2 is what is called as distinguished of degree 1, and for these special kinds of power series, you have the division algorithm. There are some things to check here. I'm not writing down the conditions, but you can find these in all kinds of books. For instance, BGR, Bosch, Baby Bosch. So therefore, Weierstrass division gives you a quotient which is in the huge power series ring S1, S2, Q1, and a remainder which is in S1, Q1, and its S2 degree should be less than the S2 degree of this thing, which means that the remainder should have S2 degree 0, means it doesn't contain any S2, such that H is Q, so dividend is Q quotient times divisor plus remainder, right? So just some theorems from periodic analysis allow you to obtain the same equation as you have in classical algebraic geometry. Now multiply this by S1. Right? Now the left hand side is divisible by S2 minus Q1 S1 by assumption. This term is divisible by S2 minus Q1 S1. Therefore, S1 minus R is divisible by S2 minus Q1 S1. But you see that S1 times R doesn't contain any S2 terms. Therefore, the only possibility is that R is 0. R is 0 means H is divisible by S2 minus Q1 S1. This proves that H is 0 in the quotient A naught. This proves that S1 is not a 0 divisor in A naught, and hence all AIs. So therefore, we have checked condition 1, that the extended ideal is invertible. Now we have to check the second condition. Yeah. So it turns out that to check the second condition, it's enough to check the second condition for affinoid Y's, because in general any rigid analytic space Y has an admissible cover by affinoids. So it has a cover by affinoids. If we check this property for each affinoid, we can glue the corresponding G maps together to get the map from Y to X tilde, right? So assume that Y is spa of R for an affinoid algebra R, and F is a map from Y to X such that the extended ideal is invertible. But we saw that that's equivalent to saying that IR tilde is invertible. So now our task is to find a map G from Y to X tilde, satisfying that commutative diagram, and to prove that G is unique. So let's start with constructing G. Yeah. So what you can do is, once you have this, you can look at the ideal AI of R, which is the colon ideal. this colon ideal. So it means all the, as everybody might know, it's all the elements in R that take the second coordinate into the first coordinate. And you look at the Zariski open sets y minus v of ai. What do I mean by v of ai here? So this is never said this is never said explicitly, but v of ai means all the maximal ideals containing ai here, because here spaces are not all prime ideals, but spaces consist of maximal ideals. So it's y minus v of ai. So take the complement. Turns out y is the union of y1 and y2, as one might expect. Because, yeah. So now we will be defining the map G on these components y1 and y2. The only problem is these y1 and y2 might not be affinoid. So it's hard to deal with non-affinoid objects. So let's take an admissible cover of these spaces by affinoids. So write y1 as the union of y1m for some m in an indexing set. For some m's in an indexing set, take y2 to be y2n. So what have we done? Here is y. Here is y1 and y2. They might not be disjoint, but I'm just drawing that for they might not be affinoid. So we break y1 into y1i's, y2 into y2n's, and we will define the map G on each such component, and then patch those maps together to get the entire map G from y to x tilde, right? So let's start with y1m. So we need two lemmas. Yeah. So yi is an admissible open set in Y. So you can talk about the value of the sheaf on yi. That's some algebra. Might not be affinoid, but that's some algebra. There is a restriction map from oy to yi, and you can extend the ideal I to this oyi. Turns out it's generated by f star si. Turns out that some uniqueness statement happens. F star si is not a zero divisor in O y prime for any admissible open y prime contained inside yi. Think of it as an open set. For any open set inside yi, you can look at oyi, and it turns out that f star si, you can think of f star si as an element of oy prime by the restriction map. Turns out it's not a zero divisor. These kinds of lemmas are proved by looking at the stocks. Stocks of various sheaves at various points. Now what do you want? You want a map from y1m to x tilde, right? So to get a map from y1m to x tilde, you can always give a map from y1m to spa ai for some ai, and then take that spa ai inside x tilde, right? So to give a map from y1m to spa ai, it's equivalent to give a map from ai to oy1m, because these two are now affinoid. So how do you give? So AI is QP S1 S2 P to the I Q1 mod S2 minus Q1 S1. Now look at OY1M. There are canonical choices of the images of S1 and S2. Those are given by F star. And you just need to give the image of Q1. So how do you give? You look at OY1M. From this property, you can see that the ideal is generated by F star S1. Ideal when extended to OY1M is generated by F star S1. Therefore, there exists a Q1 in OY1M such that F star S2 is Q1 F star S1, right? And due to lemma 2, this Q1 is unique. You can check that by taking differences. Now, Q1 is an OY1M and Y1M is an affinoid space. So, this O is an affinoid algebra. So, you can talk about the norm of Q1. So, choose, let's call it M underline. So, to match with this M, large, such that the norm of P to the M underline times Q1 is less than or equal to 1. Okay, choose M underline such that this happens, and then fix this I to be M underline. Now, the image of P to the M underline Q1 can be sent to P to the M underline little q1. So, to define a map from a Tate algebra to a different algebra, you need to send the Tate variables to elements of norm less than or equal to 1. That is why this condition is needed. So, therefore, little q1 shorthand. Then you can check that this condition is satisfied. S2 minus q1 S1 is satisfied just from the definition of q1. So, therefore, we have found out a map from AM underline to OY1M, and the images of S1 and S2 are just F star S1 and F star S2. So, by the construction, we also have the following diagram. So, this has a map, right? S1 goes to S1, S2 goes to S2. This is F star. This diagram also commutes just from the definition. So, therefore, we get Y1M to X. This is the X map. We have defined some map. Let's call it G1M. We have defined this map into SPA AM underline, which can be thought of as inside X tilde. So, we have defined a map G1M such that this diagram commutes. So, for each such part of Y, we have defined a map G, and turns out these maps glue together. Thus, we have the entire map G from Y to X tilde. Now, to finish the argument, we only need to show that this map is unique, right? But it turns out that from these conditions, maybe I can use this part. So, suppose G prime is any other map such that this diagram is commutative. You can check again by arguing at the level of stocks that G prime maps Yi inside Vi tilde. So, Yi inside the sphere minus the north pole, and Y2 inside the sphere minus the south pole, right? Yeah. So, now here is one final important trick. This, okay. So therefore G prime maps, let's say y1m. Let's take y1. It's enough to check that G prime and G agree on each such parts. So let's fix one part, y1m. So since y1m is contained in y1, G prime of y1m is contained in v1 tilde, right? And v1 tilde is a union of spa AIs, right? Since v1 tilde is obtained by gluing all these spa AIs, it turns out that this is an admissible cover. Spa AIs form an admissible cover of v1 tilde. Pulling back admissible covers gives you admissible covers again. So that's how you get an admissible cover of y1m, but y1m is an affinoid, so any admissible cover has a finite subcover by affinoids. And therefore, you can see that G prime maps y1m to finitely many spa AIs. Finitely many spa AIs, but spa AIs are nested, right? So therefore, G prime maps y1m to a single huge spa AI. So you can work with y1m. You can take a huge spa AI bigger than spa AM underline. You have this G map here, you have this G prime map here, and if I is chosen bigger, then you get a map this way, right? So to check that G and G prime agree on y1m, you just have to check that this diagram commutes. So flip all the arrows. Flip all the arrows. What do you get? A, I, and down to AM underline. And AM underline going to OY1M, right? So now under both these, so what are these? If you recall, this is S1, S2, P to the IQ1, mod the condition. Right? Under both these maps, this is what we call G prime star and G star. The images of S1 and S2 are just F star S1, S2, just from the commutativity of this diagram. So to check that this diagram commutes, you just have to check that the images of Q1 agree, right? But from the first equation, from this denominator, what do you get? You get that F star S2 is equal to G prime star Q1 F star S1. And from, if you take this equation under G star, you get a similar equation, F star S2 equals G star Q1 F star S1, right? Now, lemma 2 will tell you that G prime star Q1 and G star Q1 are equal. So therefore, we have proved that this diagram commutes. In other words, G and G prime agree. So we have checked both the properties, invertibility and the universal property. This proves that X tilde is the blow up of X at the origin.
What's the point of constructing this flow something that the identity is determined by prime axis, right?
What?
So this flow sub the flow that you're constructing,
Yeah.
the identity is determined by prime axis.
No, principle.
Oh, sorry, principal identity.
Yeah.
And this construction you have done over max spectrum of state algebra.
Yes.
So prime, what would happen over prime spectrum of state?
Yeah, so prime spectrum, there is already a construction which is analogous, just much simpler, but you get the same answer, right? The answer that I wrote. Sorry, I erased the answer. So you again get an X tilde whose points are given by S1, S2, Xi1 colon Xi2 inside X tilde of E cross P1 E such that S1 Xi2 is S2 Xi1, right? You must have seen this in Harsham. So if you apply an analogous construction to spec of polynomial algebra in two variables and the same ideal generated by the two variables, you will get something similar to this. It's just that the language here is slightly non-trivial. Instead of taking all open sets, you take only few open sets. Instead of taking all unions, you only take some special unions called admissible cover. So suppose you take a modular curve, right? And instead of blowing up in the usual geometry, so if you do it blow up in this geometry, what is the advantage? So in you take a singular, if you call in, you take a singular point. If you do not do it in the Hartshorne cells, you do it in these cells. So do you get certain advantage on that? I have not seen, I have not done that construction here. Coleman's what he is doing, so did he use this block, this kind of block? Oh, I have not read Coleman theory, sorry. Okay, so one more question. So, so all this rigid thing nowadays we can put it in addict walls, right? Yes. So you can do the same construction for the addict spaces. Yeah, there is an admissible blow up. Spa with a yes. Same construction works fine. There is a sophisticated version of talking about blow-ups in that world. Okay. You don't need to do some elementary computation like this. Okay. What's called admissible formal blow-up. It shows up a lot over there. Yeah, and there's also a version of some proj version of this construction. So there's that direction also. It's much more explicit. So when you were using the Hattie's law, yeah. So what point, singular point you were blowing up, or what point you were blowing up? What is the curve you were taking? So we are taking, so there is a space of continuous characters of QP star. So there is a rigid analytic space that parameterizes continuous characters of QP star into affinoid algebras or into finite extensions of QP. Turns out that it's given by two variables, S1 and S2, but it's slightly different than this. Then that's, yeah, so notation is T. Then, so you take two copies of T. So you get two characters of QP star, right? So one coming from here and the other coming from here. So now you look at the row bar ring over QP twisted by the action of delta 1. You take the row bar ring over QP twisted by the action of delta 2 and you form various extensions of delta 2 by delta 1. So these are what are called as two-dimensional triangulin phi gamma modules over the row bar ring. Now there is a functor from Galois representations, two-dimensional Galois representations to such phi gamma modules. And it turns out that if you take T1 and if you take two copies of T, you throw away some bad points. You throw away delta 1 and delta 2 such that the ratio is x to the minus I. X to the minus I is the continuous character of QP, right? You throw these points away and then you blow up. No, we are not going to blow up these points. These are really bad. These don't correspond to any good representations, not even geometric. So you blow up this at some good points, at all the delta 1, delta 2, such that the ratio is x to the I chi. If you make this construction, then you get some space T2 tilde. Now this space T2 tilde parameterizes all the non-split non-split rank 2 phi gamma modules over the row bar ring. This is the space studied by Kolmes and Chenevier a lot. So given any crystalline representation or semi-stable representations, these are triangulin representations, right? So if you apply Fontaine's functor D ring, you can write those representations. Sorry, this should be a phi gamma module. If you apply the Fontaine's functor D ring, to any crystalline or semi-stable representation, you can write that module as an extension of delta 2 by delta 1. That's how you get delta 1, delta 2. And this is an extension, right? So in most cases, there are no extension. I mean, there is only one extension, one non-split extension. The H1 space is mostly one-dimensional, but when the character is of the form x to the I chi, then the H1 space is two-dimensional. That's why you need to blow that up. Now, associated to each point in T2 tilde, you can associate crystalline representations and semi-stable representations to points in T2 tilde this way. And then you can talk about limits. You can take explicit sequence of crystalline representations going to some point below of this form. Then you can investigate what point does it approach to in the fiber. That's how you get some L invariant, and that's the content of Fontaine-Mazur elimination.
Thank you. It's pleasure to talk here in this seminar. Today I'll be talking about twist of GL to Fourier coefficients, and we'll see short sums of twist of GL to Fourier coefficients, and we'll get some cancellation, subwile strength cancellation in that those sum. First we'll sketch give results on this subject and try to give at the later of the my talk I'll give sketch of proof of the result. Okay, let us start with Riemann zeta function, which is given by this absolute convergence series summation n equal 1 to infinity 1 over n to the s, where s is a complex variable, real part of s is strictly more than 1, and in this region it also given by this absolutely convergent Euler product. It has a product expansion. Okay, so let us start with the Riemann zeta function, which is given by this absolute convergence series when which also having Euler product expansion when real is more than 1. And Riemann studied this function as a complex variable function, and he obtained some properties of this function. Initially it is defined in real is more than 1, since it's absolute convergent and it's uniformly convergent and complex subset real is more than 1, so it defines a analytic function real is more than 1 half plane. Then you could extend this function to the whole C meromorphically. It has a pole at s equal to 1, simple pole with residue 1, and you could establish nice symmetry of value of zeta s and zeta of 1 minus s. They are related by this factor of gamma. This is called functional equation. So if you want to study the growth of this zeta function, since it's given by real is more than 1 as the absolute convergence series, so it is bounded by 1, real is more than 1. If real is less than 0, using this relation we can and using the Stirling formula for the gamma function, we can we know the growth of zeta function when real is less than 0. The main region is that the critical strip real is between 0 and 1, the growth of zeta function, it's important to understand what is the growth of this zeta in the critical strip. So using this information of zeta, which is given by absolute convergence series in real is more than 1 and this functional equation, we know the growth of real is equal to 1 and real is equal to 0. We can interpolate that growth using the Frank-Linder principle to get the growth of this zeta in off plus IT line. That whatever bond you get using the Frank-Linder we call that convexity bond. This is the convexity bond, and here this is a single L function in this family. Here the parameter we can vary is that the S parameter. So one can define a parameter associated to zeta as a analytic conductor, which kind of measures the complexity of this zeta. So by this the bond we obtain using the Frank-Linder principle, which we call convexity bond. Here the symbol, this means this absolute value less than or equal to some constant times this quantity. That this less than epsilon means this constant may depend on epsilon. This is true for every positive epsilon. So any improvement of this exponent 1/4 is called subconvexity bond. First, while improved this bond 1/4 to 1/6, which we call it is known in literature as Weil bond. This is the Weil bond for Riemann zeta function. So it is like almost 100 years back he proved this result. After many years of people's contribution, this is the best known bond for Riemann zeta function. This is the improvement of 1/6 by 1/84, which is due to Bogen, which is in 2017, something like that. So one expects that the growth of this zeta at most due to epsilon for any epsilon positive, which is known as Lindelof hypothesis, which is itself the consequence of Riemann hypothesis. Riemann hypothesis for Riemann zeta function says that the non-trivial zeros, the zeros lie in the critical strip, all lie on the critical line offline. That is the Riemann hypothesis. So that would imply that the growth of zeta, the best growth of zeta. So this is the Weil exponent. So this is the degree 1 prototype of degree 1 L function. This is called Weil exponent. Another class of degree 1 L functions are Dirichlet L functions. Dirichlet L functions are nothing but here Riemann zeta function is defined by summation 1/n to the s. Instead of 1, you put the Dirichlet character chi n of modulo m, let's say. Then that defines Dirichlet characters are the periodic function of period m and having some multiplicative properties. And for this kind of L functions, we have again functional equation and analytic continuation and all we have. And one wants to understand the growth of this L function, this L function's growth. The yeah. Yeah, that is known. Lower bounds we know.
So it goes to infinity anyway.
Yeah, it goes to infinity. Lower bounds you mean, right? It's known. Yeah. Even if you assume Riemann hypothesis, this is the t to the epsilon. It's not. We know it is e to the power of log t by log t up to constant. That is the growth we have. If you assume Riemann hypothesis, it's better than that to the epsilon.
No, I was not asking, say, upper bound, but I was asking
lower bound also there. Yeah.
lower bound.
Yeah. Omega. It is called omega results. Yeah. Okay. So while bound for Dirichlet functions recently obtained by this Matthew Young and A.N. Petro very recently. But the analogous result of this one is kind of sub-while type bound, which is not known for general moduli for the Dirichlet functions. Suppose if I take the Dirichlet character chi modulo p to the r, fix the prime p and r tends to infinity, which we call depth aspect. In that case, Milicevic improved the sub-while strength bounds for Dirichlet functions. This is the degree 1 scenario. Degree 1 we have only sub-while bounds for the Riemann zeta function and Dirichlet characters, where not all characters, where characters are given by prime power, prime is being fixed and r power tends to infinity. In that case only we know the sub-while bounds for the Dirichlet functions. In the degree 2 case, I am giving example of a degree 2 L function here. Let us start with FB a holomorphic Hayek-Cusp form. You
Subreal bound is for a particular Dirichlet.
yes.
Right. So as you said, r tends to infinity. Is there some point converse to which you have subreal bound?
So we will get the bounds of this form. Now start with the chi modulo p to the r. Now it's like any character chi p to the r. Then you'll get L of chi, which is less than p to the power of r by 6 minus some delta. Chalk. Now we are interested in this family. Now we are varying the characters chi modulo p to the r. Now this will be like it's Cp. It depends on the prime, and p to the r. This is sub-while for some delta positive. No, we are varying the characters. This it's analogous to the Riemann zeta function case. There we don't have family, but we have family as t tends to infinity. Here we can vary prime power r tends to infinity here. Here this is the bad part. So this can be we don't have control. It's a polynomial in P. Yeah. We are only focusing on the we are fixing the t and varying the chi's. Yeah. So always we want to look the family. What parameters you want to vary or what parameters you want to fix. That is important. Now we will see in our example. We will fix the modular form f, and I'll explain here. Now look at now take the FBA holomorphic Hayek-Cusp form. Now this, let's say this is the lambda fn is the normalized Fourier coefficients. So assume that we have a del in here, right? So this modulus of lambda fn is less than or equal to n to the epsilon for every epsilon positive. Even right? So now start with this. Now take Dirichlet character chi modulus m. Now we take this series. Since this is absolute value of lambda fn is into the grows like into the epsilon. So and Dirichlet character modulus at most 1. So this defines again absolute convergence series is more than 1, and this will have a similar properties like Riemann zeta function. It is a holomorphic function whole C, and it has a functional equation and everything. Here we are f means we have weight and level also, right? We are fixing the weight and level. We are fixing the form f. Now we are varying the character chi. Now we want to vary m in terms of m. How how this L functions, and we want to fix the S also. Let's say S is equal of half. We are interested in L of F cross chi, and F being F fixed and we vary chi modulo M, we want to understand the growth of this family as chi varies modulo M. All right. So here, according to that, now if I fix the S, fix F, then this is the conductor. There is no like weight involved in this conductor. So the conductor of this L function is M square, because we are testing with F by chi. That is, chi is the conductor M, so it's M square and mod S square. Anyway, we want to take S to be like half, so it's kind of M square. The conductor of this L function as chi varying, the complexity of this L function is kind of M square. S is the this parameter. So we are looking at the central value, S is equal to half. We are interested in that value. So again, convexity bond give you M to the half. I am forgetting the epsilon part. It gives this family grows at most M to the half as chi varying modulo M. But while bound, if you assume the while bound, it's like 1/6. It's like exponent to the power of 1/6, right? Conductor to the power of 1/6 is kind of while bound, that is n to the 1/3. It's a while bound. But while bound is known only if M is a prime power, prime being fixed and R tends to infinity. In this case only while bound known for this family. But when for example, M is a prime, we don't know while bound. So yes. In general, yeah, it may vanish. Yeah, right. Yeah. Asymptotic, we don't expect individual values, but in a family average over the family, we expect the asymptotic. Yeah. So this is the state of bonds in the GL2 setup. We only know while bond. We don't know sub while. That while bond only known in the depth aspect. Prime being fixed and R tends to infinity. In this case only we know the while bound. If suppose if M is a prime, we don't know while bound even. So and T aspect while bound we know, no sub while known for GL2 setup. Okay. So using these L values, we can understand the short character sums. Here, look at this in this example. Suppose we are interested in this sum. Actually, we are interested in this lambda fn chi n and w of n by n. W is the, let's say, it's a bound function supported in interval 1 to 2, and it's a bounded derivative status. This sum is supported in the interval n to 2n actually. The trivial, if you bound this one, you get n. If you apply the triangle inequality, you get n. And you want to get cancellation in this sum. This we can study this short character. We call this kind of sums as a short character sums, because we want to take n as small as possible. So we want to understand this short character sum using the information about L values. So what we do here, this smooth function w of n by n, we apply the Mellin inversion to get the L values. So this your character sum, short character sum is related to your L values by this formula, where sigma is more than 1, n is sigma more than 1. Because W was is a bump function, so Mellin transform of W, as imaginary part tends to infinity, it decays rapidly. Always you imagine that there is no imaginary part in this integral for the for understanding. Now what you do, you shift this contour to the right of 1 to sigma equal to offline. Then you estimate trivially. Then you get this bound, because the imaginary part will be taken care of this Mellin transform of W, because it decays rapidly. Okay. Then if you shift this contour to the offline and estimate trivially, you get this bound. So one wants to understand this kind of short criteria sums. One have to understand the L values, central values of this test. Now, if you apply here convexity bond, that is m to the 1 by 2, you get this bond. It is n to the half times m to the half. But we know the trivial bond is at most n. But we got the bond n to the half times m to the half. But it is non-trivial only if n is more than m. This bond will be non-trivial if we want this to be strictly less than n, that would give you n is more than m. But we want to take n as small as m to the some small power of delta, small power of m. We want to take n, we want to take much smaller than m. That is our m. Okay. Suppose now I am fixing my conductor m to be a prime. In this case, we don't know Weil strength bond for that L values. But if you assume the Weil strength bond for this L value, you will get this kind of bond, like p to the power of 1/3, that is a Weil bond. This is non-trivial, that means it is strictly less than n if and only if n is more than like p to the 2/3. Okay, it's like your m is p here, like m to the 2/3. Convexity bond will give you like n more than m, while give you like n is, you can take m to the 2/3. You are lowering the size of n. So without going to the information about L function, because it is proving Weil bound for general characters here hard, it's not known. But without going to use information about L values, we can directly study this kind of sums by another methods to get better bonds. Indeed, Aritra Ghosh is a student at IISER Kolkata. He studied this sum when chi is a prime moduli. Then he could obtain cancellation in this kind of sum, kind of whatever Weil give you. So he could show this kind of bond. If you see, this is non-trivial if and only if n is at least p to the 2/3, which is same as the kind of Weil strength. Weil strength. So our aim is to show sub-Weil strength bonds for this kind of sums when chi is given by p to the r, p fixed and r tends to infinity. Now in this case, let us say m is a power of prime. I am fixing the prime p and r is varying. In this setup, Weil bound will give you this cancellation in the short character sum if n is more than p to the r to the 2/3. We know the Weil bound for this kind of L values in this setup, but we want to get cancellation this short character sum when n is smaller than this value. Yeah. So sub-Weil bond for this L value would give you cancellation in this sum if n is smaller than 2/3 here. These sums are studied by Blomer and Milskevich, and they obtained when m is the prime power, they could obtain this kind of bonds, which is non-trivial. Again, n is more than p power r to the 2/3, which is kind of Weil strength again. So our aim is to improve their bond. We are improving the not bond, but we are getting the shorter cancellation in the shorter sums than the Blomer and Mirskovich. So this is our main result. This is the joint work with Aritra Ghosh. We have this short character sum is bounded by n to the power of 5 over 9 p to the 13 r by 45, provided our n should satisfy this condition. Note that this bound is non-trivial if n is more than or equal to this one. We could beat while bound by 1 over 60. Okay, this is a depth aspect, but there is a we are testing real to Fourier quotient by character of prime power moduli, but there is an analytic twist version which was studied by Ritarbata Munshi, Zicki and Roman Holansky, and they could beat while bond in the analytic twist aspect. So here f is fixed, chi is varying, but chi the power of prime power is varying for me. Conductor. P is fixed, like let's say 5 or 6 7, let's say. Yeah, yeah. Capital N given a prime, yeah, R is varying, so N is varying. So this is a counterpart of an analytic twist of GL2 Fourier coefficients. So we could obtain similar kind of bonds for analytic twist. Okay. So is it fine up to here about results?
This game, particular F doesn't give you anything better. Either you do it for all F or you do it for none.
Yeah, yeah, right.
I mean, there is no nice, people study nice examples where something is clearly true and then they like to think about it in general. But in this game, if one puts F to be the Ramanujan delta, it doesn't.
Yeah, no, it's the same thing, same result. Yeah.
And F needs to be
Yeah, F is holomorphic. We use if we use Delian estimate, because if it's not holomorphic, it's kind of divisor function you need to take, but it works for the divisor function case also, I think. The Fourier coefficient given by the divisor functions, no? Essence, yeah. Mass forms, you're talking about mass forms. Oh, mass forms, it is true. We don't use Delian and individually, but we use Delian and average, L2 average. We use this kind of bonds. Yes, exactly. Because to simplify my argument, I am assuming the we use this. This is known. For mass forms, it's known. Yeah, it's asymptotical N actually. Yeah, we use this this kind of Ramanujan for the quotient. Yeah, we don't use Ramanujan. To explain, I'm just assuming Ramanujan. Means here, yeah. Okay. So rest of my talk, I'll give proof of this estimate. So I'll hide this smooth part here by writing this n is asymptotically like n. This means let's imagine this kind of sum running from n to 2n. There is a always floating a smooth part here. So we want to understand this sum. Here we use delta method, which is developed by Richard Munshi. By studying this kind of sums, delta method approach is useful. I'll explain his method here in this setup. So what we want to understand this sum, we can understand this sum, we cannot understand this sum when they are together. What we do, we separate this lambda fn chi n by using the delta method, delta symbol. What is delta? Delta is a Dirac delta function which is integer to r, which is defined as follows. If m is 0, it is 1, m is not equal to 0, it is 0. Now, we want to find out a nice expression for this delta before applying here. That is already found by Duke, Filner, Ivanich. The delta expression is roughly given by this one. Suppose your n is in interval, let's say minus m to m. You want to detect when n is 0 or not. Okay, your n is in this interval and you want to detect when your n is 0 or not. And in that setup, if you choose your q, capital Q to be square root of this m, this kind of size of your n, small n, it is roughly m. If you choose capital Q to be of square root of m, then you delta n is roughly given by this symbol. Here now observe that delta of m minus n, now you want to detect m equal to n or not. Now delta of m minus n, if I put here, it will be like a of n minus m by q. Because of additive character here, e of a n by q times e of minus a m by q. The m and n variable get separated. Here they are in the together in a subtract form, but they are kind of separated there. That is the important fact. So here is the setup. We are separating this lambda fn Fourier coefficients and display character values by writing this symbol. This is 0 unless n minus m by p to the l equal to 0, that is same as n equal to m, we get the original sum. But instead of writing just delta of n minus m, we wrote like we divided by p to the l here, and we put a condition p to the l divides n minus m here. Here L is a parameter such that p to the L less than or equal to n and L is less than or equal to 2r by 3. This is important in our setup. Initially we start with L is less than or equal to r, but it turned out to be that L should be less than or equal to r by 3. So why we are introducing this extra divisibility condition is follows. Already chi is the modulo p to the r. So there kind of arithmetic conductor is there, p to the r. So you can introduce extra things here like p to the l that won't complexify the situation by introducing this extra divisibility, which you call conductor lowering. Now because of this, if you look at this equation n minus m by p to the l, the size of this n minus m by p to the l is given by n by p to the l roughly. So we want to detect this equation by this symbol. Now you want to choose your n minus m by p to the l is size n by p to the l. Now you can choose your q to be n by p to the l here. By choosing your q square root of n by p to the l, and by writing the expression for delta, this expression here, and you detect this divisibility condition by the additive characters, you end up with this expression roughly. Your original sum look like this one. Here the advantage is that the Fourier coefficient sum and your district character sum get separated. Now what we can do here is that we can apply the summation formulas to individual sums to get kind of shorter sums. When you dualize them, you get the different lengths. So here is the Poisson summation formula. If f is a, let's say, sparse class function, we have a kind of summation over fn and summation over f hat, and this same. It's a Poisson summation formula. It's a f hat is the Fourier transform of f, and Warner summation formula. This kind of sums transform to this, and Hn is a Hankel transform, which is given by this one. This is Bessel function. And here Bessel function, think of it roughly look like jk of x roughly look like 1 by square root of x times e of plus or minus x. It look like that. Now using these two summation formulas, if you apply here Warner summation formula on this n sum and Poisson summation formula on m sum, you get this one. If you apply the Poisson summation formula on m sum, you get this expression. Here this integral transform will determine your dual lengths, sums of dual lengths, lengths of dual lengths, dual sum, sorry. Here tau chi is the Gauss sum, which absolute value is p to the r by 2, and your a variable is getting determined by m. Once m is fixed, your a is determined. That a was given here. Okay. So by Poisson summation formula, we transform this whole sum into this sum. This is the, after simplification, we get the character sum. You find out what is the value of character sum, and this is the expression you get finally. It roughly look like that. And if you apply the Warner summation formula on this n sum, you get this expression for n sum. If you write to all together, your original sum roughly look there like this. Because you don't have anything to do, only one thing, just you dualize them. Yeah, we get savings by applying overnight, because the savings, you have to understand the always sums. You don't think about forget about the coefficients. Always this complexity of the sums involves the conductor and lengths of sums. So generally, when you apply the overnight, you save initial length, that is n by square root of the conductor. Conductor is like here p to the 2l q square. That much you save. So you have to see which way it will work. But generally it works initially, because we are separating them. So we have a large length, and yeah. So conductor lowering, right. So that works in the, suppose there is no p to the l here. Here n sum would be better here, because it's a lot here in the n sum. But that help would be in this sum, not in this sum. We are losing here, but not here. Right. Suppose we are introducing conductor lowering. By conductor lowering, we are losing here, but we are gaining here, because already p to the r kind of oscillations, arithmetic oscillations are available here, chi modulo p to the r. So we could introduce extra oscillations, p to the l type. That won't change. Okay. So your sum roughly look like this. Here, what we do, we this is the complex. This is the hard part. So we remove this part by applying the Cauchy squares. So here we get this kind of sums. When you apply the Cauchy squares and n sum, you get lambda fn square. This kind of bounds you have to use here while applying the Cauchy squares and n sum. So once you apply the Cauchy squares and n sum, your sum will be looking like this. where theta is given by this, where the Fourier coefficients are now removed from the original sum. Now here this kind of GL2 kind of problem, by applying the Cauchy squares and we remove the Fourier coefficients, we are making the this kind of again GL1 problem. We are reducing the complexity again here. So what we do here again, we open the absolute square and introducing the sum. We look at the sum over n. Before that, you smooth the sum and open the absolute value square and look at the sum over n. The sum over n look roughly like this. Okay. Now again we have a kind of sum over n. Again you apply the Poisson summation formula to this sum. Then once you apply the Poisson summation formula, your resulting sum look like this one. Sorry? This one. After applying the Cauchy squares. Yeah. So, yeah. So, yeah, Voronoi, Poisson, Voronoi, Cauchy, Poisson. Voronoi we apply on GL2. See here Voronoi, Poisson. Yeah. Yeah, remove the lambda part by applying the Cauchy. Yes. You apply the yeah, here you remove the GL2 Fourier equation by applying, yeah. You get this one, again apply on n sum your Poisson. Okay. Then your sum will look like this one. Okay. But here what we can, here you have to treat two cases where when n is 0 or not. When n is 0, what happens is that in the zero frequency, that is called with zero frequency, here we cannot save much than the number of diagonals in this absolute value. The number of terms in here, that is q times m. We only save q times m, number of harmonics inside the absolute value in the zero frequency. We cannot expect more than that. So when n is 0, that is we get q equal to q prime and m equal to m1 equal to m2. q1 equal to q2 and m1 equal to m2 you get, and you get the diagonal saving there. So we cannot do anything better than saving the diagonals in the zero frequency. If you do that by n equal to 0 putting here, and you get the q1 equal to q2 and m1 equal to m2, and you estimate this by assuming q1 equal to q2, m1 equal to m2, you get this kind of bond for your theta. If substitute theta bond here, which corresponds to your zero frequency, you get the bond for your original sum, which is kind of contribution for zero frequency. So this is the best you can do in the zero frequency. You cannot do better than that. What we can do in the non-zero frequency, here when n is non-zero, what we can do, here we have a congruence equations. We write the equations. So this is the alpha 1, alpha 2 are variable modulo p to the L. You by writing one variable into another, like I am writing here alpha 2 in terms of alpha 1 like this, and m1 equal to m1 is congruent to this one modulo q1, m2 congruent to this one modulo q2, because we have this equation, right. Now here we determined alpha 2 in terms of alpha 1, that's okay. We saved p to the L in the alpha sums. Here in this congruence, write the equation like m1 equal to this plus some r1 times q1, where r1 is a variable now. We are changing the m1 variable into r1 variable and m2 variable into r2 variable by writing the congruence into equations. Now you observe that this r1, r2 variable have size this one, p to the r by n. Now n is of size p to the r, we don't have size, we don't have lengths of the summations of ri's. But if you assume n is much smaller than p to the r, that's why we are counting n is less than or equal to n to p to the 4r by 5, we are taking that condition. So we have lengths for this Ri sums. Now we are changing the variable m1 m2 into r1 r2. Your sum in the non-zero frequency look like this one. Okay. Now we can expect some cancellation on the r1, either r1 or r2 sums here, because r1 r2 sum these sums having some size. We can expect some cancellation here because they are oscillator terms. Before that, we have to take care of this alpha sum. We want to get square root cancellation in this alpha sum plus some extra cancellation in this r1, either r1 or r2 sums. That would give you sub-while. If you take the here square root cancellation of alpha sum, that is easy. Then you will get the while kind of thing. Plus, if you do extra here, you will get the sub-while. So first we get square root cancellation in alpha sums. First, what is alpha sum? Let us look at. The alpha sum is given by this one. Here we will use the fact that chi is a Dirichlet character modulo p to the r. So the Dirichlet characters modulo prime powers, they are given by this exponential time. Here we are taking the quadratic polynomial in z variable here, because our choice of L is less than or equal to r by 3. So by writing the expression for chi in terms of the exponential, we can evaluate this sum, because it's a complete character sum modulo prime power. Prime power, it's easier to evaluate, get square root cancellation is easy. So to get, we know chi of 1 plus this one, we have kind of formula. So what we do, we take out this factor r1 r2 take out, r2 r2 take out, we get 1 plus this r1 q1 bar type this way. Then you write the value for chi here, and you evaluate exactly the alpha sum. So after doing that, you get square root cancellation, because this trivial leads to p to the L. If you evaluate this p to the L, after evaluating that, it is a p to the L by 2 times this one. Its absolute value is 1. So you are getting the square root cancellation plus exact things, how these terms behave in terms of r1 r2, because we want to take care of r1 r2 sums as well. So here this is a nice function we get after evaluation of the alpha sum, but we get the condition on r1 r2. So r2 times r1 bar is square modulo p. That means we cannot expect cancellation both sum r1 r2, but either one, either r1 or r2, because we have a condition, they are not independent anymore. So we want to look at the r2 sum now. Up to here we get the while. We want to do something extra to get sub while. So we want, for that we want to get some extra cancellation, either r1 or r2 sum. We are looking at the r2 sum. The r2 sum looks like this. Now we want to get some extra cancellation here. G is some kind of phase function involving all kind of these kind of things. I am calling it G. Okay. So again, because of this square condition, we are splitting into this kind of moduli, various Congress classes. It doesn't bother much. So your sum look like this one exactly here. You can evaluate this one. Your R2 sum is given by this one. This is the main part. Okay. Your phase function f look like this one. It's kind of it's a periodic logarithm. It's kind of just normal expansion only. It's kind of polynomial because power of p to the r here, because p is involved here, where the finitely many terms only contributes. Now here we want to get some extra cancellation to get cancellation over R2 sum. That we can do, we can achieve by applying periodic exponent pair to this inner sum. So what is the periodic exponent pair? So in Milicevic, in a GL1 setup, when he was studying the depth aspect, chi Dirichlet character modulo p to the r, when he was proving the sub-while thing, he could obtained periodic analog of exponent pair. What is the periodic exponent pair? Now KL is said to be periodic exponent pair with this condition. If these kind of sums is bounded by this this p to the n minus w kappa by b to the k and b to the l. This is the length of the sum, and this kind of these numbers come from here. The derivative of f roughly look like this one. Then this sum is bounded by this thing. Then we say this k and l periodic exponent pair. Whenever your phase function satisfies this derivative condition, then your sum should be bounded by this one. Then we say k l is periodic exponent pair. And he could list some list of periodic exponent pair in his paper, but this is relevant to us in our situation here. Sorry, this one. UV kind of some some integers which are co-prime to P. Use the number, yeah, not a function. Here you take the derivative. Here it's kind of yeah. Hmm? Some they are fixed some numbers which is co-prime to P, let's say. Okay. So we this is definition, like KL is said to be periodic exponent pair. Whenever f satisfies this condition, you will have this bond. That is the definition. So you apply that this 1 over 30 and 13 over 15, the periodic exponent pair in this setup. This is relevant to us. This pair will save us something. So if you apply that periodic exponent pair here, you get the R2 sum. This is at most this. Here we save something in R2 sum. Then if you write all the bonds back in the expression for your sum, you get this kind of bond. Now you have to choose your L is a parameter. Now you can choose optimally by equating the contribution for a zero frequency and non-zero frequency. So here, then you get the value of L. Yeah, either one of the value is your bond for your original sum, that is given by this. Thank you. Yeah. Huh? Yeah, right. Here. This is the important step actually, because by writing chi in terms of exponential, that is important step actually. Not p to the z square, z in z variable. Yeah. Yes. Okay.
So this is for a specific mechanism.
Yeah.
Can you expect better bounds if you average over all the
Um, Average. Um, yeah, but average you want to take. Yeah, right, right. We can apply the Peterson. Yeah, but I don't know. But um, but it's interesting study. I think no one study. I think we can study this one also. Looks like. So what you can do, you can take f is in HK. No, not the without absolute value. You take the absolute value square actually of let's say f. Now you want to get kind of um, Lindelof on average. That you can expect, right? So it's kind of k. Let's say you are wearing the weight, and it's kind of yeah. You want to do this one? Average, but how this chi is varying here? Yeah. We use only the transformation property, overnight summation formula, automorphy. Yeah, of lambda with coefficients, right? I can show you here. Where is this? This one. This is the kind of it follows from the automorphic condition for your f. Yeah, any coefficient, not only model form. This kind of replace this coefficient, but you find some kind of transformation properties. Like you can you if you dualize the sums into this kind of sums, that will work. Any some function, some smooth function, any function, smooth function. Yeah, yeah, because here we need to transfer smoothness needed to study this kind of angle transform. No, it is a consequence of automorphy of your f. It's kind of functional equation. Functional equation itself is a consequence of automorphy, right? So that's all we use actually. Yeah, functional equation. Yeah. Yeah, and I mean, what the all Fourier coefficients, some coefficients having nice transformation property. Then k is the weight, yes, weight of your form. K is the holomorph. But analogous formula also there for mass forms. It's you get IT, you get the spectral parameter will come there. Yeah. No, only lambda because we separated already here. It doesn't see each other. Don't see each other. Yeah. Because the purpose is that we want to study their correlation. Initially they're seeing each other, but by separating, they cannot see each other, right? So we can study them separately by applying this approach. No. Kuznetsov is kind of here. It's kind of orthogonality of your Fourier coefficients. Like you study this, let's say lambda fn, let's say you're averaging over f with some weight lambda f, some inverse something. Now it's kind of orthogonality of this kind of, it's kind of delta of n minus m place some involving Krustromer sums and all, some C, S, N, M, C by C, some J Bessel function will come. This is a trace formula says how they are orthogonal actually. This kind of orthogonally. Even Munshi sir, he did using this symbol. See, here delta is appearing here. Now you can use this. It's called GL2 harmonics. Now you can write delta expression for delta using the GL2 harmonics. This minus this is equal to your delta. Now by writing this in your problem, you can study. Now you can use the information about this one. It's kind of GL2. He calls GL2 delta. He did in his paper, analysis paper, with this approach. So yeah, trace formulas also give some expressions for your delta, higher in terms of the higher harmonics. We are using the GL1 harmonics, right? Here your delta you are writing in terms of the E of something only. There is no higher coefficients like GL2, GL3. We can write using the trace formulas like Kuznetsov, Peterson. We can express delta in terms of the higher harmonics. That may also help, but yeah, he is working, I think, Munshi sir, using the GL3 Kuznetsov to write this delta and studying the GL4 problem.